Hi, we're in chapter 15. Guy Lusick and Avogadro to the rescue. Now we must return to Mr. Dalton. Just when things seemed to be clearing up, they got muddled again. We recall that John Dalton was certainly on the right track, but then in getting the right way of going about things established relative atomic weights. He got entangled in errors not only about the weights themselves, but about the number of atoms and what he was attempting to weigh. As in the way with most things, the one error made the other worse. During the early part of the 19th century, the time of Dalton, the weighing of elements and compounds was simple, but simply not very accurate. And if there are inaccuracies made in the relative weight of an element, oxygen, for example, then those mistakes will carry over into all the other calculations that depend on the first. That is exactly what happened. For example, if, as Dalton did, we miscalculate the relative weight of oxygen and water, which consists of hydrogen and oxygen, as 7, and then use that weight to calculate the weight of carbon and carbonic acid, which consists of carbon and oxygen, then the mistake with the oxygen carries over into the relative weight of carbon. Just as with arithmetic, the miscalculations run like falling dominoes through all the other calculations. A significant part of the inaccuracy in calculating relative weight was caused by another more serious problem. If you make a mistake like Dalton's about the number of atoms in a compound, then the mistake will run through all the other calculations as well. It will only make inaccuracies in weighing the elements in compounds all the worse. For example, because Dalton thought that water was made up of one atom of hydrogen and one atom of oxygen, he miscalculated the relative weight of oxygen. For water, as we now know, is made up of 2 hydrogen atoms, not 1. To understand Mr. Dalton's error, let's return to the magic marble sorter that helped us understand how relative atomic weight was calculated. Remember that the black and white marbles are too small either to see or to weigh individually. Now suppose that the sorter sorts the black and white marbles with the following units. The bucket of white marbles weighs 1 pound, and the bucket of black marbles weighs 7 pounds. Could you conclude that the weight of black marbles relative to the weight of white marbles was 7? The answer is no. Why not? You cannot assume that there are the same number of marbles in each bucket. Remember, they are too small to see. If there really were 100 marbles in the one bucket and 100 black marbles in the other, then you could conclude that the weight of the black marbles relative to the weight of the white marbles was 7. But what if you found out that there are actually 200 white marbles in one bucket and 100 black marbles in the other? Then what is the relative weight of the black marbles? The white marbles actually weigh half of what you had originally thought, which is the same as saying the black marbles weigh twice as much. So instead of the relative weight of the black marble being 7, it should actually be 14. To return to the example of water, Dalton's error lay in assuming that there was only 1 hydrogen atom in water. Since we now know there are really 2, then the individual hydrogen atoms actually weigh half of what Dalton had thought, which is the same as saying the oxygen atom is twice as heavy, with a relative weight of 14, not 7. Now, the relative weight of 14 for oxygen is much, much closer to the relative weight of the 15.9994 of oxygen we use today. But we are looking ahead. At the time, none of this was clear, so both problems had to be fixed by better weighing techniques and by an accurate grasp of the number of atoms of each element in a compound. It took about 52 years to sort it all out. During that time, chemists used all kinds of weights for elements and could not agree on the number of atoms in a compound. Things got so confused, and chemists had a great deal of trouble talking to each other. The man who first helped to sort things out was Joseph Louis Gay-Lussac, a French man. In fact, Monsieur Gay-Lussac published a paper that would help to clear things up in 1808, the very year that Dalton published his famous New System of Chemical Philosophy. But as seems to be the case more than once in the history of science, the answers do not yet look like an answer, because chemists had not wrestled with the difficulties long enough yet to get in the questions asked in the exact way. What did Gay-Lussac discover? Monsieur Gay-Lussac worked. Okay, what did Gay-Lussac discover? Monsieur Gay-Lussac, with the combination of combining volumes of gases, noticed he was working with volumes, not as Dalton with weights. He discovered something which reminded him of the observations of Proust. He noticed that the combining volumes of gas always seemed to turn out to be whole numbers. He found that 2 volumes of carbonic oxide combined with 1 volume of oxygen to make 2 volumes of carbonic acid. He noticed that 2 volumes of hydrogen and 1 volume of oxygen made 2 volumes of water in the form of steam, the gaseous form of water. He observed that 3 volumes of hydrogen and 1 volume of nitrogen made 2 volumes of ammonia. All whole numbers, not a little bit over 1 volume of oxygen in carbonic acid, or just a tad under 2 volumes of hydrogen in water, or just a flea's eyelash over 1.1259303, 2 volumes of nitrogen in ammonia, but 1, 2, and 1 exactly, all whole numbers. Very strange. Furthermore, this soon led some to wonder whether equal volumes of different gases under similar conditions of temperatures and pressures might contain the same number of particles. Why might such a notion occur? Well, if you had 1 volume of hydrogen and 1 volume of chlorine, which at the time they called oxygenated muriatic acid, and they combined to make 2 volumes of hydrogen chloride, which they called muriatic acid, and might think that there would be exactly the same number of hydrogen atoms as chlorine atoms in the equal volumes. But other things did not add up so nicely. To return to our previous example, if you think that equal volumes of different gases might contain the same number of particles, then this should happen. 1 volume of carbonic acid plus 1 volume of oxygen equals 2 volumes of carbonic acid. But that is not what Gay-Lussac actually found. He found that 2 volumes of carbonic acid plus 1 volume of oxygen equals 2 volumes of carbonic acid. In fact, as lovely as Monsieur Gay-Lussac's experiment results were, no one could make sense of them. Except one man, the Italian Amedeo Avogadro. Amedeo Avogadro published his answer in 1811, just 3 years after Dalton's book and Gay-Lussac's paper. He shouted the answer, but no one heard him. In fact, no one recognized the importance of his answer until 1860, almost 50 years later, when chemists were so fed up with all the problems and confusing plaguing chemistry that they called an international meeting. There, another Italian, Stanislao Cannizzaro, who did see the significance of Avogadro's answer, handed out a short pamphlet explaining it to the other chemists. Ah, they said, now we see. What did Avogadro see that cleared up the vision of his fellow chemists? The equal volumes of gases do indeed contain equal numbers of atoms, but some atoms travel in pairs. Once we realize that, declared Avogadro, we solve all the problems with Gay-Lussac's strange combining volumes and all the problems with figuring out atomic weights too. It all makes sense when we realize that. For example, oxygen likes to travel in pairs. So when we return to our example, 2 volumes of carbonic acid plus 1 volume of oxygen equals 2 volumes of carbonic acid, and write it in modern symbols. 2 CO2 plus 1 O2 equals 2 CO2. Notice there's 2 C's and 2 O's when you look through. Everything adds up perfectly. In the 1 volume oxygen, there were actually twice as many oxygen atoms as anyone had supposed. So if you have 1,000 COs in a volume, you would have 2,000 COs in 2 volumes. And if you had 1,000 O's in 1 volume, you would actually have 2 times 1,000 individual oxygen atoms, or 2,000. Just enough to match up with the 2,000 total COs to make exactly 2 volumes of carbon dioxide. And hydrogen likes to travel in pairs as well, which is easy to see in regards to volumes of water as steam produced in their union. So we have 2 hydrogens plus there's going to be 4 oxygens if you see, or hydrogens I mean, plus 2 oxygens equals 4 hydrogen and 2 oxygen. Okay? And nitrogen likes to travel in pairs too, as we see with hydrogen and nitrogen combined to form ammonia. Finally, chlorine likes to travel in pairs as well. So what was really going on when chlorine combines with hydrogen was this. One hydrogen, which has 2 hydrogens, and one chlorine, which has 2 chlorines, equals 2 hydrogen chlorines. Once it was discovered that some elements always travel in pairs, and chemists have gotten more accurate calculations of the percentages of elements by weighing in compounds, then things all fell into place. To turn the example of water, better calculations of the percentages of weight of oxygen, hydrogen, and water were available in the mid-19th century. They found that water is 88.8% oxygen and 11.2% hydrogen. Recalling the chemists were calculating the weight of oxygen in relation to hydrogen. If we divide 88.8 by 11.2, we arrive at 7.92857 rounded off. But when we realize that there are 2 hydrogen atoms and 1 oxygen atom in each water molecule, we know that 2 hydrogen atoms make up 11.2% of the weight. So a hydrogen atom will weigh half this amount, which is the same as saying that 1 oxygen atom will weigh twice as much. And 2 times 7.92875 is 15.857, which is very close to our contemporary relative weight of oxygen, which is 15.9994. Fancy that it took so long to figure out just what water was made of. Wouldn't the Dallies be proud? As chemists accept the insights of Avogadro and use them to sort things out, they came into more and more agreement the atomic weights of elements, and the more agreement there was, the more accurately the atomic weights could be calculated. We are now very, very close to our modern periodic table of elements, and you may have even had a whisper of a hint about the next step, a step both so gigantic and so simple that allow the elements to be put in a definite order. If you have all the elements and each one has an atomic weight, you might wonder if there is some kind of pattern to the atomic weights, some kind of beautiful, marvelous order just waiting as a kind of intellectual treasure to be discovered. 16 things fall into places, triads and octaves. Sometimes scientists try to make headway and everything becomes more disordered and confusing, but sometimes scientists find far more order than they ever thought possible. Such times fill scientists with awe and wonder, as if they had gone digging for a few precious stones and uncovered the vast treasures of a pharaoh. And that's precisely what happened when chemists started to look for patterns in the atomic weights of the various elements. They were doing a very humane thing. Human beings, especially scientists, but also philosophers and theologians, are always suspicious. They have a deep down feeling that things are not just put together randomly, a strange intuition that underneath it all there is a conspiracy going on, a great conspiracy of order. That's why chemists started to wonder and wonder, as Aristotle said long ago, is the beginning of all science. So without knowing in advance whether it would lead to anything, chemists started to look for patterns among the elements, first small patterns, then large patterns. Johann Wolfgang Dobereiner noticed that what he called triads. These were 3 elements, where the atomic weight of the middle element was approximately the mean of the lightest and heaviest of the 3. To make this clear, let us look at his triads: calcium, strontium, and barium. The weights Dobereiner used were calcium 27.5, strontium 50, and barium 72.5. The mean is 57.25, which you get by adding the 2 extremes and dividing by 2. Well, that's about 50, the approximate atomic weight of strontium that he used. And Dobereiner thought it marvelous, especially when he found other triads. We'll put them in very vertical rows. Okay, so you can see them there. Little did he know they had stumbled upon a gold mine. If you look at the periodic table today, you can see Dobereiner's triads running in vertical rows. On your table, the vertical rows are called groups, and the horizontal rows are called periods. So we'll use these terms from here on out. Li, Na, and K lined up very nicely right under hydrogen. In the next vertical row or group, the one with beryllium, and on the top we find, after magnesium, calcium, SR, and Ba line up just like buttons on a coat. Then scan over to the right-hand side of the table to the group headed by oxygen, and right under it, lined up beautifully just like all the others, you will find S, Se, and Te. Go to the next group to the right of S, and you'll find Cl, and under it, Br and I. Marvelous indeed! We should note, however, that Doberer-Einer calculations were made on the basis of atomic weights before things were straightened out by Avogadro's insights. But interestingly enough, Doberer-Einer found the right relations even in the wrong weights. To return to our first triad, to accept atomic weight of calcium today is 40.08, and barium's atomic weight is 137.34. Yet the mean of the two is 88.71, which is close to our accepted atomic weight of strontium, 87.62. The other triads listed above also worked out fairly well, so he noticed the right relation even if the atomic weights he used were in need of repair. Before you jump to conclusions, such nice calculations don't work everywhere. So, Doberer-Einer discovery was marvelous indeed. He did not know how marvelous it was, for the structure of the table, the way the elements lined up so precisely in groups and periods, had yet to be deciphered. He made a very good beginning, however. Chemists tried to find all kinds of other relationships, always looking for patterns between the atomic weight and similarities in the properties of the elements. The single most important advance allowing chemists to find such patterns as we may have guessed was the use of Cannizzaro and others of Avogadro's insights, which had cleared up all the confusions in regard to atomic weights. With this leap in accuracy, at a little past the midpoint of the 19th century, came great intellectual leaps as well. John Newlands made a major leap forward by taking quite an obvious step forward. He simply looked to the known elements and arranged them one after another in order of increasing atomic weight, and numbered them accordingly, 1, 2, 3, 4, and so on, all the way up to 51. When he did, he noticed something rather odd. Every eighth element had similar properties, at least roughly similar properties. He called it the law of octaves, because the eighth element, starting from a given one, is a kind of repetition of the first, like in the eighth note in the octave of music, do, re, mi, fa, sol, la, ti, do, or as in the letters starting with the middle C on a piano, D, E, F, G, A, B, C. Every eighth note seemed to be a kind of a repeat, since it shared similar properties with the first. Now let's take a look at his table and see not only how well he did, but how he accidentally stumbled upon the very heart of the order of the table of elements, without noticing it, however, merely by numbering the elements in accordance with increasing weight. I've tilted Mr. Newland's table on the side so that elements run in the direction of our table today. I've also included only part of it, the part which he got right. The rest of his table was not nearly as accurate. Note that we have put Roman numerals above each group, but we begin with 7. Then we go to 1, 2, and so on all the way up to 6. These are not Newland's numbers, but correspond to the group numbers we use today, which you find by looking at the top of the table. If you take hydrogen out and lay it to the side and lift group 7 up and put it down again where it belongs, to the right group, F6 and F next to O, we see an amazing correspondence to our table. Again, we brought Newlands to the discovery of the law of octaves. Was not just lining the elements up by decreasing atomic weight, lightest to heaviest, but seeing the similar properties of every eighth element. So whatever element you choose, if you count from it, like notes on a scale, either up or down, you end up with the same group above or below the element from which you started. For example, all the elements in group 1, Li, Na, and K are metals and are very, very reactive. They latch onto other elements and form compounds so quickly that they are never found alone in nature. Furthermore, a drop of water in one of them will cause a violent reaction, even an explosion. Today we call this group the alkali metal. All the elements in group 2 likewise have similar properties. They are also metals and quite reactive. Today we call them alkaline earth metals. Leaving hydrogen aside, the elements in group 7 are all called Halogens, which means salt formers because they readily combine with metals to make salts, the most famous being table salt, sodium chloride. Very good. Now for Mr. Newland's accidental discovery. By numbering the elements according to their increasing atomic weight, Mr. Newland accidentally stumbled upon the very heart of the order of the periodic table of elements. If you look on today's table, you will see that the elements are numbered in horizontal rows or periods beginning with H as 1 and going all the way up to MT, metanurium, which is number 109. These are the atomic numbers. As we shall see in the next chapter, the atomic number, not the atomic weight, is the real key to the table's wonderful order. At the time, no one, not even Mr. Newlands himself, could see how merely numbering the elements in that way might be such a glorious key to unlocking the mystery of the periodic table of elements. Chemists simply did not know enough yet. To return to Mr. Newland's law of Octavius. When he didn't present it publicly, he struck a sour note, or rather quite a few. As said above, we have included only part of his table, about 1/3 of it. The rest of it was not so very accurate. A sign of this, even to chemists of this day, was that elements in the groups in the other 2/3 of the chart he suggested as similar were not actually all that similar. Poor John Newlands, a Mr. Cary Foster, whose only claim to fame is the one comment sarcastically asked Newland if he had thought of alphabetizing the elements instead. But Newland was on the right track. Mr. Cary Foster, to the contrary, in fact his elements would have lined up much better if he had only used the first draft of his chart instead of the second. In the first draft he left spaces, gaps, where there were jumps in atomic weight. He was too timid to leave such blanks in space in his second draft. The one he read before the members of the Chemical Society, which include Mr. Foster among the audience. After all, if he had blank spaces, it would look as if there were holes in his chart where elements should be, blank spaces representing elements unknown but waiting to be discovered. Such a thing would be bold. It would be outrageous. Predicting the discovery of unknown elements by their atomic weight, such a thing was unheard of until along came Dmitri Ivanovich Mendeleev, who did that very thing. Mr. Newlands might today be heralded as the discoverer of the periodic table of elements, only he had not filled in those blank spaces, putting something where there was nothing. In this instance, the nothing was something more important than he had ever guessed. All right, I'll see you next time. Bye.